like really kind of understanding how this is all worked out this semester, you could just do this times that, right? Because we had this property way back in the beginning that said if you have a double integral, you've got two variables in there, and the functions in here are completely separate from one another, like the r function, the theta function are separated by multiplication, then you can split it into two and multiply the answers. So you can do it this way also, right? And then this one right here should just work out to be 2 pi. And then this one we have to work out. Okay, so I'm going to go ahead and say, this is 2 pi, everyone, right? Do I need to go through that work? I don't need to go through that, right? 2 pi? 2 pi times, and then now we need to do the integral 1 to 3 of r root 1 plus 4r squared dr. So basic u substitution here, right? Like u would be 1 plus 4r squared, du would be 8r dr. I don't have 8r dr, I have just r dr, so I go 1/8 du equals r dr. So that integral up there rewritten becomes 1/8, I lost myself, u to the half du. Then the antiderivative, do y'all understand? I'm expecting you could do this, but I'm kind of showing some of it here. This is going to be 2 pi. The antiderivative of this is going to be 2/3, right? 2/3, so 1, I can't do it. 2/3, 1/12, thank you, 1/12. And then u, right, to the 3 halves, but u is 1 plus 4r squared to the 3 halves, evaluated from 1 to 3. So you plug in 3, you plug in 1, subtract, you get the answer. I'll stop there. I don't feel like plugging those in. All right? Any questions? Do you want to see the answer numerically, computer? Just so you can. Okay. Can I use this one? I think we went 1 to 3, we went 0 to 2 pi. We did r times the square root, 1 plus 4r squared. Oh, oops. R times square root, 1 plus 4r squared. We did d theta dr. See, it's a nasty looking number. So I'll do it as a decimal instead. 111.988. So I was thinking about something this weekend. That's a very special double integral. What does that give you?
That gives you volume.
This is the area, right, of D, right? That's the area of D. What does the triple integral over E of 1 dV give you?
Volume.
That's the volume of E, right? Yes? Then what does the single integral of 1 d, let's say, x give you?
Gives you a variable.
Volume area length. This would give you the length of, yeah, so we usually put in Cal 2 our limits of integration, right, from A to B.
Yeah.
And isn't your answer here just B minus A? Isn't that just the length of the interval?
Yes.
Yeah. So this gives you the length of the interval of integration. Does that make more sense now backwards?
Yes.
So like this one gave you the area of that domain, D. This gave you the volume of the domain, E. This gives you the length of the domain, which is that little line segment on the number line. So long as this is 1, these are constants there, right? The reason, what made me think of that was this one right here. We just had this problem. And we said the answer was 2 pi, right?
Yeah.
That's basically integrating 1. And so this is basically the length of this little interval, which is 2 pi minus 0. All right. And we move along.
All right.
That's it.
56 bonus. Wait, what? 56 bonus and final? Wait, what? The numbers 56 bonus turned in.
Number 56 from the book is a bonus question to be turned in at the final if you're interested. This is out of 13.6. Not like you don't have enough to do. Boy, starting to really get to the end of this thing. So number 56 says, well, it gives you a figure. Yeah, I'm not going to be able to draw it here. Well, let me see what that was. I don't think that was the drawing. No, that's not the drawing. Maybe here? No, that's not it. What are these?
I have a question.
Yes.
So you know how you said we can turn in our homework at the end? Would you be able to get that?
The binder?
Yeah.
Oh, I'm just going to be checking it to look that you like have work for the semester.
get it back after.
Yeah, I'll give it to you the same day. Yep. Yeah, that's like an extra couple of points, right? Something like
5
that.
points overall, I said.
Right, because you can have a total of 105, I believe, in this class. So if you don't turn in the binder, you don't get penalized, but if you turn it in, it's like a 5-point bonus.
I was just wondering, 'cause
Yeah.
I have to keep going.
Yeah, I'll give it back to you. Okay. Now, the next thing we're going to do, we're going to step away from the book for a minute and step away from the notes that are on the web. I have a handout for you. So here's the next progression of things is to get into 13.7. The problem with 13.7 is that at this point they expect that you are now masters at drawing surfaces with these new vector functions. Okay, so like if I gave you a surface, you'd be completely comfortable coming up with the R of UV for it. Now all we looked at was really like a sphere, right? That was the only example I really gave us. So what I have is a handout here where we're going to have, well, let me hand it out. I hope I have enough. I could, and you could share too. Sharing is caring.
No, I don't care, but I don't care.
Yes, well, that becomes an issue. Let's see. Oh man, I think I'm going to be short. 1, 2. Where'd you all come from? There's 3 there. 1. Can you all share that for now? Okay. Is that okay? Did I not give you all enough? Can you all share one? I honestly just have no more copies. All right, so here's what we're going to do. You have in front of you a document that gives you a surface, and we have to come up with the vector equation for it. In other words, we need to come up with the R of uv. And the first one, I actually give you a little more information than I have up here. I tell you that x squared plus z squared must be less than or equal to 4, and then I tell you that y is what? Y is 0? Is that what's there?
Yes.
Okay. So this is the actual surface right here. And we need to come up with the vector equation R of uv that will draw this. All right?
Okay.
All right. So this is a disk, isn't it?
Yes.
It's not a circle, it's a disk. It's everything in there. And there's something about it that is always the same. What's always the same with this disk? Your y. Your y is always 0, right?
Correct.
So when you come to do this with your component functions, you can say that the middle one is 0, right? That's for sure. Now, how do you draw the circle? Well, how do we draw the disk? How do we draw circles? Because you could look at a disk as just being a circle with that radius, then a circle with the radius a little smaller, then a little smaller, and then a little smaller. So these are our grid curves. How do we draw a bunch of circles that get smaller and smaller and smaller? Not spiraling, but each circle, the radius gets smaller. So, and what is the widest diameter, or what is the widest radius circle we have? 2, right? And the smallest would be 0. So how would you draw me a circle of radius 2? If I asked you to draw me a circle of radius 2 with the parametric function, you would use sine and cosine, or cosine and sine, wouldn't you?
Yeah.
So if I put, don't write this down, but if I write 2 cosine, let's say u, 2 sine u, and I let my u go between 0 and 2 pi, that would draw me just the outside, right? Just the outer edge?
Yeah. Yes.
Okay? But see, I have control over 2 variables now. I can control 2 things, not just one. So I still have my v to work with, right? I have a v that I can control, and I should use that to control which part? The radius, right? So instead of using 2 and fixing it, I should let the radius be v, and then let my v go between 0 to 2. Does that make sense? So imagine if v was 0, you would have 0, 0, 0, and you'd have the origin. Then if you let v be a little bit bigger than 0 and fix it, you'll have a little radius, and you draw the circle. And then as you let it go out, it's going to start drawing bigger and bigger circles until you get to 2, and then you have the whole disk. Make sense? Okay, that's the first example. That's the cleanest, prettiest one. All right. Let's move to the next one. Find the vector functions, plural. See that? Functions, plural, which yield the 4 face surfaces of the tetrahedron with the vertices 0, 0, 0, 3, 0, 0, 0, 4, 0, and 0, 2, 0, 0, 2. All right? So we need to be able to come up with 4 separate vector functions, 4 separate ones that will draw each of the 4 surfaces here. Right? Okay. Y'all ready to do it? Let me label some points here. This is the point 3, 0, 0. This is the point 0, 4, 0. And this one up here is the point 0, 0, 2. And then the origin's in there, right? 0, 0, 0. All right. We have 4 surfaces, right?
Yes.
So we got to label them. So here we go. I'm going to label. Let's start with the surface that's underneath on the bottom there, right? The bottom side of this. Let's call that S1. Let's call the back side over here S2. The back side over here S3. And then this actual front side, let's call it S4. We do know 3, but we need to get everything written down perfectly for them, all right? So let's talk about S1. S1 is basically the ground, isn't it?
Yes. Yeah.
And if we were to draw it, it would look like this. This would be our X, right? This would be our Y. It would hit out here at 3 here. It would hit the Y-axis at 4 here. We're trying to draw this surface right there, right? Okay. But we need to do it with the vector function, r of uv, and I'm going to make it r subscript 1 because it's the first of 4 surfaces I'm going to have to draw, right? Okay, is there any nice part of S1? Anything that we're really happy about with S1? Z is 0, right? Z is 0? Because it's on the ground, right? So Z is 0, that part, pretty straightforward. And then I have control over 2 variables now. So when you look at this surface, how can you draw this?
You can have UV. No, wait, no, makes sense.
Okay, so what about if I let my x coordinate be u, okay? That would be this part, right? And that would go between where and where? 0 to 3. Okay, this next part is super critical, all right? This next part is super, super critical. What would then your y coordinate be? I heard someone say v. Yeah? Is that what I heard? Yeah. Okay, let's just see. If it's v then, let's just go with this. If the y coordinate is v, then what would the restrictions on v have to be?
0 to the function.
So I let my u vary between here and here, right? But if I were to fix a u, right? Let's say I pick some u value between here and here. Let's say I fix it right there. There's where I am. Then my v has to stick between there and there, right? Between that point and that point. So it's between 0, right? And that curve or that straight line segment, which is actually a function of u, right? And what is it as a function of u? It's negative 4/3 u plus 4. So it's the line, it's the equation of that line, right? But replacing x with u. Do y'all follow that? This is critical because here's the mistakes that I see sometimes. Sometimes I'll see people do, v here, and then on the restrictions they'll just put, 0 to 4. I hope that's obvious that that's wrong because that's gonna give you the rectangle, isn't it?
Yeah.
It's everything, all the x's are between 0 and 3 and the y's are between 0 and 4. That doesn't work, right? Okay, what other things do I see? What if someone did this? I'm just curious. What if someone did this? They said, u is u. This is negative 4/3 u plus 4, 0. And they said that u is between 0 and 3. Would that work?
No, because where should be?
Because it would only give you the outside, inside.
Yeah, so the big difference between this is critical, all right? So if you have a question on this, make sure you ask now. This first one says, this is the correct one. It says, fix me a u, boom, and now my v can go anywhere between 0 and that value, right? So now my v can be everything in there. And then I just keep moving my u. I get everything between, like that, right? And I get the whole shaded region. if you do this, right, and you don't say anything about v, then fix me a u. If you fix me a u, what happens? Fix me a u, like let's say right here. And then what's your y coordinate? It's just that point. It's not the stuff between it. So all that would do is draw you that one line. Right? So that doesn't work. We have to incorporate both variables somehow for this to draw us a surface. All right, what about S2? I'm going to draw another picture for S2. Now I have the x and z plane, don't I? S2. It's along this backside. So it's kind of like I've walked around to the side. I'm looking at it from the backside. It hits the x-axis at 4. Where does it hit the y-axis or z-axis? Up at 2? So we have basically the same sort of thing, don't we?
It's at 3.
It is at 3. Yeah, it is at 3. Why did I say 4? Oh, because there's a 4. No, I looked at that 4 actually. I just looked at that 4. Everything's off. I moved my picture and now everything is off. That's no excuse. I can't seem to get it back to where it was. Well, maybe I can scroll this way. Where is it? Close enough. Okay, now here, what can we say about this second surface, r subscript 2, which is the easy part here? Y is 0, okay, because you're in the xz plane. So y is 0. Okay, then what are you going to let the x be?
X is just going to be u.
Let x be u, and u will go between 0 and 3 again, and let your z this time be just v. And v will be between, so you fix me a u somewhere in here. Now I want everything between here and here. So I want my v, which is my z coordinate, which is my up and down, to go between 0 and that thing. And what is that thing? Negative 2/3 u plus 2. You get it?
Yeah.
Okay. All right, S3, this should go fast. S3, our picture looks like this. We have the y-axis and the z-axis. It hits the y at 4. It hits the z at 2. That was the one that... Okay, so we want this stuff in here. So my third function, R3 of uv, should be... Okay, what's the easy one on this one? X is 0, right? The y and the z, I get to choose here. What do you want to do?
We'll have u y.
U is going to be the y, and u will go between 0 to 4, and then our v will be the z coordinate, and that will go between 0 and that line again. So 0 and negative 1/2 u plus 2. I don't know if you can tell from my code here. When I'm plotting these, I'm telling my computer, look, I want, which is the one we just did. That's this one right here. I said, okay, look, I want to do what's called a parametric three-dimensional plot. Here's my vector function. It's 0, u, and v. My u is between 0 and 4, and my v is between 0 and negative 1/2 u plus 2. So I'm telling the computer exactly what the surface is that I want it to draw. And that drew me S3, which is that backside. Okay, so these are the 3 we've done. This is the last one, all right? So let's see what this last one turns out to be. S4 is, I think, the more challenging. Why is S4 the more challenging one? Yeah, when you look at S4, Let me erase all this stuff. Okay, y'all there? Y'all paying attention? Okay. I want us to look at S4 from above. S4 from above looks exactly like what? S1. Doesn't it look like S1? Okay, what was S1? The vector function for S1, y'all can tell me, it was UV0, right? And then we had restrictions on U were between 0 and 3, and V was between 0 and negative 4/3 U plus 4, right? That drew me S1. What is the big difference between S1 and S4? What is the huge difference? Because they look exactly the same from above. Z is not 0, right? Z actually depends on U and V. So when I draw this, or when I start to come up with a function, I know that these two are the same. U and V, the x and the y, are the same thing because that's what draws S1. It's this part right here can no longer be 0. It has to be whatever gets me from the ground up to that surface, right? I'm going to come along. That doesn't help. In fact, my restrictions are still the same. So what? How do I get that Z? That's right, we have to find the plane equation. We actually have to find the equation of that plane. Because the equation of that plane depends on x and y, doesn't it?
Which you'll just give us, right?
Which I will just give you. I will give you the vertices of the plane. I will give you these. So we've done this way back since chapter 10, right? So let's just look at these. This was 300. This one was 040, and this one was 002. And so now I need two vectors, right? I need to cross them, and then I can get a normal, and then I can use any of those 3 points. Then I have my plane equation that I solve for z, and then that's my function of x and y.
Yeah.
Yes, okay. So I don't know, I'm just going to choose, I'm going to go this way. Here's one vector, and here's my other vector. So I'll call this v1. I'll call this v2. All right, so v1, the vector v1 is the vector 3, 0, negative 2. And my vector v2 is the vector 0, 4, negative 2. And when I cross these two, I get, what, 8, right? 0, minus, minus, so, no, wait, why did I minus that twice? I don't know why I did that. I should just, oh yeah, because it's minus, yes. 8, and then negative 6, so 6, and then this last one we get 0. Is that right? No, that last one's not 0. What's that last one? 12, okay. There we go. So what is the equation of the plane? So this plane has the equation 8, and then x minus what? You get to choose, right? Which point? I'm going to go with 300. That's the one I'm going to use. So x minus 3 plus 6 times y minus 0 plus 12 times z minus 0 equals 0. 8x minus 24 plus 6y plus 12z equals 0. And yeah, I could have taken a 2 a long time ago. I just decided not. I was going to do it way back when we had the cross product. I was just going to say, hey, we may as well use like 4, 3, 6, but now I solve this for z, don't I? Okay, let me solve it for z. So if I solve this for z, I get, let's see, negative 8x over 12 minus 6y over 12, and then plus 24 over 12. So I moved all these terms to the other side, divided everything by 12. That reduces out z equals negative 2/3 x minus 1/2 y plus 2. Someone please check. Am I doing that right?
Yes.
Yes? Okay. I can check with my own work up here to make sure it's right. But okay, that's what I get for z, right? So now what we do is, this is z, right? Z depends on x and y, but we know the x is really u, right? And the y is really v. So if I plug that in right here, negative 2/3 u minus 1/2 v plus 2, that will draw it. Now look, I think it's important for you to understand what's going on here. So what I'm going to do is I'm going to take this out. I'm going to cut this out of here. And let me run this now. Let me run this. Let me take all this crap out of here. Okay, so what's happening to draw this surface? Why is that backside there? I guess it's just showing a shadow. Trying to get a good perspective on this. Hold on, do I have a polygon here somewhere?
Yeah,
I do have a polygon. Shoot. I have so many polygons here. I need the one that goes 0, 0, 3, 0.
Or you mean the one that's
00300.
This one right here. I need this one out. Cut that one. Try and run it again. There we go. That should. Stop it. Stop it. There we go. I think that might be a little bit better. Okay, so look, this is our x-axis, this is our y-axis, right? What we're saying is, if you pick a u, right, that's our x, pick me a u, then what you're going to do is you're going to let your v be all the values between 0 and negative 4/3 u plus 4, which means all your y values are going to come from here, right?
Yep.
And then what are all your z values going to be? Your z values are going to be living on this surface. So imagine taking this line segment and mapping each point up onto the surface right there. And what you will create is just that grid line. That will be your grid curve. And if I move u over a little bit more, take all those, plug those in, we'll do that one. If we do all these together, it's going to draw me the whole plane. Okay? Hope that makes sense. All right. Moving on to the next one. So I think I wrote something down here for you, didn't I? So what did I tell you on there? I gave you the picture and then I said what? You see? X squared plus z squared equals what?
1.
X squared plus z squared equals 1. Y is between 1 and 4. This is a cylinder, yes? It's hollow. How do we draw this? Can we draw it all in one shot? Can we do this with one function? Is this a single surface? Yes? I'm getting nods of yes. Okay, if so, you're going to need to convince me by coming up with the vector function. What do you want x to be? Cosine u. Now you're doing one cosine u, so you're saying that this is going to draw a circle of radius, I think you're going circle of radius 1, which is this, right? Okay, what else? Z is sine u. Everyone agree that if I just did that with u between 0 and 2 pi, I'm going to draw a circle of radius 1.
Yes.
This is just going to tell me where I need to draw that, like where my y coordinate needs to be. And where does it need to be?
It needs
From 1 to 4.
It needs to be every circle that goes from 1 to 4. So I need to draw like this circle, then move a little bit, this one, this one, this one, this one, this one. So what is this going to be? This will be V, right? And V will be between, I think 1 to 4, right? 1 to 4? So if V is 1, you're going to draw a unit circle back here at the back, right? If V is 4, you're going to draw this front circle. And if V is everything in between, then you're going to draw all the circles between there. Make sense? That one's not too bad, no? Okay. What about that one? This time we want everything here. We want I want not only the cylinder, I want this front face and the back face. Although on my picture it doesn't look like there's a back face on that.
Because you got rid of the thing. No, wait,
No, I hadn't, not on this one. I hadn't deleted anything. So for this one, if I want the cylinder, the front face, and the back face, how many will I need? Can I do it all with one? Mm-mm. No, I'm going to have to do this with 3 different ones. Right? How can you possibly draw this front face? The way you draw that front face is the first example we did.
Yes.
Right? The way you draw this one is that one.
The third one is going to be the other.
And the third one's the back side, which is like the first one. So, okay, let's then just call this one R1. Okay? And it's exactly the same, isn't it? I think it is. Does it still go from 1 to 4? Yeah, 1 to 4. Did I say to do? Oh, just the end cap. I'm sorry. So I just want that front side. I apologize. I just want this piece right here.
Oh, so you just want the end cap?
Yeah, so we can do this with 2.
Okay.
This one will draw the blue part, right? It's the one the previous example. So the red end cap, we'll call that the second surface. I want the red end cap. What is that? Do we use cosine u, sine u again? Yes and no. It'll have to be v cosine u, and then v sine u for the final one. And then what about your y? Because your y, you don't have any more variables. It's fixed at 4 because we want just that end cap. Your u will go between 0 and 2 pi. And your v will go between what? 0 and whatever the radius of this thing is, right? What's the radius of this? Was it? I don't remember. Was it 1? 1? So the v controls the radius of the circles, the u controls the drawing of the circles, and your y coordinate is stuck at 4. Yes?
If you draw a solid, would you add another variable? Like instead of u would be another variable?
So you're asking this. What if you had u, v, w, right? And you have some 3-dimensional vector where x is some function of u, v, w, and y is some function of u, v, w, right? Blah, blah, blah. What do you think? Think you can draw solids that way? Yeah, you could, because you could just do something like u, v, w, very simple vector function. Let this be between 2 constants, that between 2 constants, that between 2 constants. You'll draw a box. Wouldn't you?
Yes.
Yeah. I feel like y'all are getting the hang of this.
I hope I am.
Okay.
I feel like I am. I hope I am.
What about this one? So I have some information here You see, can I see that real quick? X squared plus z squared less than or equal to 1. Y is equal to 0. X squared plus z squared equals 1. And x plus y minus z equals 2. So I'm giving you some information here. Here's what I want though. I'm going to spin this around, then we're going to take a break. We have a cylinder that's very similar to the problem we just did, right? That blue part. The difference is that the back side of this is not at 1. It's up against the xz plane. Do y'all see that? It's at y equals 0. And then the other part of it is that the front cap here is no longer like flat. It's got an angle to it. And that angle is controlled by that plane right there. So it's like this plane is cutting through, like this. Okay? So this right here, x squared plus z squared is less than or equal to 1 with y being 0 is the back cap. Okay? The x squared plus z squared equals 1 is the blue part, and then the plane is this part. So here's what we'll do. It's 3:40. Let's take a 10-minute break, all right? We'll go to it's 3:41. We'll go to 3:51, and then once you come back at 3:51, we'll go to 4 o'clock and see if y'all can get these 3 surfaces, okay? And then we're going to go around, and I'm going to ask randomly for someone to give me their surface. And if you get it wrong, you fail the class.
Wait.
I'm kidding.
What do we do?
If you get it right, nothing happens. You get to continue.
Oh, and then if we get it wrong?
You fail the class.
Oh, okay.